Hi folks, Chris McClure here. We now are going to push into section 5.3, talking about our very first distribution. Now that we know what a probability distribution is, and that distribution is going to be the binomial probability distribution, one of the discrete distributions that we're talking about here in the course. We're going to talk about the basic definition of the binomial distribution along with notation, methods for finding binomial probability values. Now, the reason that we would be using the binomial distribution is in which we have repeated trials of an experiment in which there are just two possible outcomes. So what am I talking about? Here's an example. Suppose that we flip a coin. There's only two possible outcomes, getting the heads or tails. Now, just flipping a coin is just a very simple experiment. But suppose we have several trials of it, meaning we flip a coin multiple times, 10 times, 20 times, a million times, whatever. And at each time that we flip a coin, we are going to record whether it's a heads or a tail. So now we have a kind of a compound experiment in which we are going to observe the total number of heads and tails. Generically speaking, we talk about successes and failures. The binomial probability is going to calculate the probability of achieving a certain number of successes or failures, however you want to call it. The random variable x is going to be that number of successes out of n number of trials. Okay. So in order for us to be using the binomial probability distribution, we need the following requirements. First of all, we have a fixed number of trials. It's not elastic. We know exactly how many trials were done. That each trial must be independent of each other. Think coin flips, right? Each coin flip is independent of any other coin flip. And each trial must have all outcomes classified into either a success or a failure, one of two categories. The probability of success remains constant. That goes along with the independence. Meaning, for example, that for a coin flip, it's going to remain 0.5 and 0.5 for the probability of heads or tails at each coin flip. That's not going to change. Now, you could do approximately a binomial when you are taking a sample from a large population, but you're sampling without replacement, because those probabilities from one draw of the marble or whatever to the next is not going to change much at all. The notation that we're going to use, of course, the capital P means probability of some event, as in success, in this case, probability of a success. And we're going to just generically call that probability of P, as in the letter P, probability P. Probability of failure, we'll call that Q. And P plus Q must be equal to 1, because the complement of a success is a failure, and the probability of a success plus the probability of the complement of success must be equal to 1. So if you know what P is, then 1 minus P is going to be what Q is. The letter N is going to denote the fixed number of trials. Think about N being the sample size. Typically, that's what N is. X is going to be the random variable which counts the number of successes out of N number of trials. P, the little p here, will be the probability of a single success in a trial. Q is the probability of a failure in one trial. This capital P of X means the probability that random variable X is going to be a certain number of successes. out of n trials. And just to be sure, x is going to count the number of successes. Little p is going to be the probability of one success. So whatever outcome you're calling a success, x and p needs to be referring to the same sort of category. And this second bullet here goes back to what I had just told you earlier. If you are sampling marbles from a huge bag of marbles and I have two colors, and you're going to let x count the number of white marbles, for example, that you've drawn in a sample which is much smaller, less than 5% of the total number of marbles in the bag, then you could use a binomial probability to approximately compute your probabilities, provided that your sample size is less than 5% of the population, because those events will be approximately independent of each other. So here's an example of a binomial sort of experiment when we are going to randomly sample some adults and ask them whether or not they know what Twitter is. Well, we know from previous experiment that about 85% of the population knows what Twitter is. So that means if we randomly sample one adult, there's an 85% that he or she will know what Twitter is. Now we're going to do a little experiment where we're going to randomly select 5 adults from somewhere. Could be in the grocery store, could be on Facebook, could be at the bingo hall, at the VFW, wherever. We're going to randomly select 5 adults, and we're going to ask each of them the same question: do you know what Twitter is? And the probability that 3 of the 5 adults will know what Twitter is, we'll do that calculation here in a few minutes. But that's an example of a binomial sort of experiment. And yes, this procedure will result in a binomial distribution, because there will be a certain probability that 0 people will know what Twitter is, or 1 person, or 2, or 3, or 4, or 5. I'll show you how to calculate each of those individual probabilities. And thus we would have a binomial distribution. There are 5 trials which are independent. Each trial has 2 outcomes, meaning the person either does or does not know what Twitter is. And there is a constant probability of 0.85 for each individual. Because our sample, 5 individuals, much, much, much smaller than the population of all adults. So how do we calculate binomial probabilities? Well, I'm going to highlight 3, but I'm going to show you 2 calculational ways of doing it. So first of all, here's the mathematical formula. I know it looks kind of scary right now, but I'll show you how to use this formula to calculate your binomial probability. This tells you that the probability for X number of successes out of n number of trials is going to be n factorial divided by the product of n minus x factorial, which, by the way, is the number of failures. So number of failures factorial times successes factorial times the probability p of one success raised to the x power times q, which is the probability of one failure, raised to the n minus x power. Okay, and this distribution is going to be for x being between 0 and n. That's going to be the range of values for x. In other words, the domain of this probability function. Okay, so here's the formula. Here's what each of those letters mean. I saw a funny little meme on Facebook yesterday that said something like, there was algebra, and then Satan decided to introduce the alphabet into algebra, which is already a difficult topic as it is. So But no, these letters of the alphabet are really just numbers. Now, you could use various statistical platforms, StatDisk, Minitab, SPSS, Excel, TI-83 Plus calculator. I'm pretty sure everybody has access to Microsoft Excel, TI-83, TI-84, TI-85, 6, 9, Inspire. There's lots of different Texas Instruments calculators that can do this, as well as HP and Casio and many others. I'll show you how to do the binomial calculation on the TI-83. Or you can look it up using the appendix. I'm not going to really show this to you because you have access to technology. That's what I'm going to show you. So use your graphing calculator whenever possible. Only if you are hard up and you don't have access to a computer should you use that appendix in the back. Again, I'm not going to show that to you. I'm just going to show you the graphing calculator. I'll show you how to use the calculator to evaluate that probability function. And I'll also show you the shortcut using the distribution menu. Okay? So here's an example here. Here's our one example that I'll show you. Every other example is very similar. You need to know the number of trials, which in this example here, there are 5 trials. And then you want to calculate the probability of having 3 successes. That's what X is. And you need to know the probability of having a success for one trial, which is 0.85 in this case. So we'll say a little p is 0.85. And that means that probability that someone doesn't know Twitter is 0.15. So that's what Q is. And we want to calculate the probability of having 3 successes. That's what this notation is. Now, if you want to use your pencil and paper together with a calculator and use the formula, then you'll have P of 3. Probability of having 3 successes is going to be 5 factorial. Remember, 5 is the number of successes, divided by 2 factorial, 3 factorial, times 0.85 cubed, times 0.15 squared. And then just simplify all that. I'm going to jump over to my calculator here. And here's my calculator. Let's do that calculation. I'm going to do my open parentheses 5 math probability, and option 4 is the factorial. And then we're going to divide that by, and in parentheses I'm going to put 2 factorial, which by the way is 2 because it's 2 times 1, times 3 factorial. 3 factorial is 3 times 2 times 1, which is 6. So I'm going to just put a 6 down there. Close parentheses, and then times 0.85 cubed times 0.15 squared, and then enter. And if we did it right, our probability works out to be approximately 0.138. Okay? Now, here's going to be an easier, more slick way of doing the same calculation. Is the TI-83 and TI-84 have these various probability distribution functions already programmed. If you go into your distribution menu, just go hit second and this button here, and then go and scroll down under the distribution submenu, and I think it's going to be option A. There you go, option A, binomial PDF. PDF means probability distribution function. You're going to put 3 numbers in. The first number is going to be the number of trials, which is 5 in this case, parenthesis or a comma. And then the second number is going to be the probability of a single success, which is 0.85 in this case, comma. And then the last number is going to be the number of successes, which is 3 in this case. Close parentheses, enter, and voila, you get the same number. I recommend that you become familiar with binomial PDF command. That'll make your life pretty easy, or at least a lot easier compared to computing from the formula like you see here. Okay, so there's your computation of binomial probability. Now the reason that we have this formula is this n factorial over n minus x factorial times x factorial is going to really count the number of ways that you could get x number of successes out of n number of trials. Because after all, that's a combination. Doesn't really matter what order the successes come in. That's why we use the combination. And then the p to the x times q to the n minus x will calculate the probability that for any one set of x number of successes and n minus x number of failures, of having that number of successes and failures, of having x failures and n minus x failures and x successes. So just to illustrate this, think about p to the x power as p times p times p times dot 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 out to p. X number of times. There's x p's there. And q to the n minus x power, that's going to be, q times itself n minus x times. What does that really mean? So let me actually jump over on my tablet and pull out my pen. And so, for example, I don't know. Suppose that I'm going to, let me pull out my pen here. I'm going to roll a fair die, let's say 10 times. And, you're either going to roll a 1 or not roll a 1. And we're going to let x be equal to the number of 1s that come up out of 10 rolls of the die. Now, the probability of rolling 1, 1 is going to be what? Well, there are 10 rolls of the die, so we have 10 factorial divided by. Now, there's going to be 9 rolls of the dice that do not roll in 1. So 10 minus 1 is 9, and then we have 1 factorial. So this right here will count the number of ways that I could have gotten 1 out of 10 rolls of the die without respect to order. Now the probability that for any roll of the die that it came up with the 1 is a 1/6, and there was one of them. The probability for any one roll of the die that it came up not a 1 would be 5/6, and there were 9 times that happened. Okay, because of the fact, you see this right here, because of the fact that the probability of having a 1 is 1/6. That could happen anywhere on the first roll, second roll, third roll, fourth roll, or whatever, all the way up to the 10th roll. All the other rolls are non-1s, and their probability is 5/6. And because of the fact that each roll of the die is independent of each other, all you need to do is calculate their individual, or calculate the product, I should say, of their individual probabilities. So regardless if your first roll was a 1, or the last roll was a 1, or any other roll of the die between roll 1 and roll 10 was a 1, doesn't matter where in that sequence of rolls that you end up with a 1, that probability is 1/6 for that roll, and 5/6 for all the other rolls. You just multiply them out. You would have 1/6 times 5/6 times 5/6 times 5/6 dot dot dot. Okay, that's why we have this. So that right there is binomial probability in a nutshell. You'll have the chance to practice this on your homework. Now, today is Tuesday, June 17th, 2014. I still need responses from about half the class to tell me where you are taking your test. I've sent out a couple of emails. Several days ago, well, at least a few days ago, I put out a blank practice midterm exam. Yesterday, I put out the solutions. Actually, I think it was earlier today. Yeah, earlier today I put out the practice solutions. And then I just sent out an email with specific instructions about taking your midterm exam. So you're going to have a 1-week window to get to your testing location or get with your proctor and take your midterm exam, and then have that test returned to me, preferably by scanning and emailing. But I'll accept a fax, and I'll also accept it snail mail. Snail mail is less preferable because it takes a while. At least when I get your test, I will grade it almost immediately. It's in all of our interest to make sure that you have a score with immediate feedback. Lastly, I've posted midterm grade. It was due tomorrow to the college, and it's only based on your homework that you have done or haven't done. Okay, it's not based on anything else because I don't have exam scores yet. Okay, so when you see that score posted on Blackboard and also posted with the web info system, don't be too shocked if you see a score that you're not expecting if you haven't been doing much in the way of homework. All right, so we'll leave it there for now. We'll continue with this discussion on probability distributions next time, okay? Have a good day.